Hello everyone. So let's continue our discussion of neural network parameterizations. So let's first recall where we were. Something is sorry, there's some technical issue. What has been- Okay, I think now it should be fine. Okay. Yeah, now it's fine. Okay, so here was the setup. So we had a neural network with a bunch of layers. So we have a bunch of layers. And then by the word parameterization, we meant that how do the various parameters change with respect to n? So what is the correct scaling of parameters? So more specifically, so what should be the scaling of the initialization, the learning rate? Yeah. So what should be the scaling of these things relative to the weights? Relative to weights. Yeah. So there's a big question we wanted to answer. And to make it a bit more precise, we use the word ABC parameters where A, so where weights go as n to the minus A, initialization, variance goes as n to the minus 2B, and the learning rate goes as n to the minus C. And we saw some examples of this. So examples with our the neural tangent kernel or neural tangent parameterization, where you set A1 equal to 0 and AL equal to half for L at least, for L more than 1, BL equal to 0, and C equal to 0. And here, if you recall, because of this AL equal to half, it so happens that your weights don't change much. So weights stay close to initialization. And therefore you will not learn features. In other words, this also lies in what's called the kernel regime. Essentially, this means that your whatever function your network learns is equivalent to doing essentially a kernel SVM. Okay, so equivalent to Okay, let me not use the word SVM because that means classification. But yeah, essentially it's just doing it's only a linear function after kernelization. Okay, yeah. So yeah, so we saw this. Yeah, and then we also saw the mean field, or yeah, MF. So here you set, yeah, again A1 0, A2 1, but crucially you set uh, so B is still 0, but crucially you set C to -1. So this high learning rate, so this essentially causes the training to move out of this no feature learning regime, and yeah, then it will yeah, cause feature learning essentially. Yeah, so we saw all of this in the simplified setting of one hidden layer. That's just easy to write down. One hidden layer. Yeah. So today also we will yeah, talk further about this, but we will not talk about two hidden layers. Let's see what happens. And by the way, we also talked about what's called the standard parameterization, which is similar behavior as mean field for one hidden layer. The standard.
Is it similar? Standard also the rates don't change.
No, they do.
Okay.
Yeah. So okay. So I guess it depends on. Okay. So we had just one hidden layer.
No.
Yeah, but okay. Yeah. So when you more hidden layers, yeah, that's what we will talk about today. But okay. So maybe let's just talk about more hidden layers. That's an interesting case. Anyway, so let's see what happens. Okay. So let's go to two hidden layers.
You change the rate.
Okay. Okay. So to make things easy, let's assume that our phi is identity. Because when you have two hidden layers, then it's hard to write down things if phi is not an identity. So let's make it an identity. And yeah, and yeah, let's talk about standard parameterization, where yeah, so AL is 0. Uh, yeah, for all L, B1 is 0, and BL is a half for L than 1. Yeah. So that's the standard parameterization. And now you want to really ask what learning rate should be set. So what should C be? So what values can C take? Okay, so anyway, so maybe let's first begin writing down our equations. So let's recall what our notation was. So we had something like, so here's our function f, and now there are two hidden layers. So let's call the logits here as h. Okay, okay. So after second hidden layer, it's f, of course. Okay, so okay, I think the picture is more confusing. Let me just try it in notation. So you have a function f equal to some matrix V times h bar. H bar is some matrix W times H, and H is some matrix U times your input Z. Okay, so yeah, now there are three matrices instead of two as last time. Good. And and now let's ask what the initialization is for these matrices. So U alpha beta. So any entry of U is from standard normal. So standard Gaussian with Gaussian with mean zero and variance what?
Generally, how sensitive are these things to these initializations? I mean, suppose one just keeps a mean and variance fixed. Does the distribution really matter that much? You know?
Probably not, but the variance really matters.
Variance matters.
Yeah.
Yeah. So then, there's a guidance that comes with how to select it.
Yeah, exactly. So that's what we will talk about.
So you will keep everything linear now, just to keep things simple.
Yeah. Right now, because when you have two hidden layers, then it becomes very complicated if it's not linear. So this is like intro. So
Yeah, that's
great. Okay. So from the notation A, B, C, A and B. So what's the variance here? It's one. So yeah. So majorly the variance is n to the minus BL, n to the minus 2BL. Where L is a layer number. So B1 is 0, so variance is 1. And what about W alpha beta and V alpha beta? What's the variance now?
1.
Yeah, 1 over n. Yeah, again by the notation. Good. Okay, so now let's write down what would happen when you run STD. Okay. So of course, after initialization, so like we also pointed out last time, just by using center limit theorem kind of argument, because these U, V, W are standard normal Gaussians, your F, H bar and H would all be Gaussian processes also. For large n, right? So as last time we pointed out, these will have roughly IRD Gaussian with variance what? So coordinates, these are, and what's the variance of a coordinate? It's not very hard. So I'm using multiplication, right? So there are no tricks.
It should be like non-liquid.
Sorry? Yeah, let's assume that your Z is a constant. Your input Z is some.
So then H should be because
Okay, so let's just write down. Let's just do this computation. So H is U times V. So yeah, so more specifically, if we take a coordinate of H, so what does the coordinate look like? It's some row of U interproducted with the right. So the entry of H, any entry Hi looks like some UI. So yeah, some row of UI. So some row of the matrix U interproducted with. So if I were to find the variance of this, then I will just add up the variances of the UIs, and that is 1, because so for every U the variance is 1. Every entry of U the variance is 1.
Your dimension, size of number of entries of Z is also fixed. You're not changing it at time.
Yeah, so right now think of Z as a constant, right? I mean it's literally
Just a number.
number, just a number, right?
Yeah. Then just yeah. Minus 1.
Yeah, so it's just 1.
So Z is normalized or?
No, so right now Z is just univariate.
Oh, it's just one variable.
Yeah, yeah, you're just keeping everything easy. So here F and yeah, I think first one last class. So F and Z are, let's say, univariate. Okay, so yeah, so variance of H is 1. What about variance of H bar of any entry in H bar?
So if Z the constant doesn't get multiplied,
So its variance will be like Z.
Yeah, so I mean, I'm thinking of that as some.
You should write theta 1.
Yeah, theta 1, yeah, I'm being a bit sloppy. So, but I don't mean exactly that. But it's theta 1. Yeah. Okay, right, theta 1.
you're talking like Greg Glenn.
Sorry?
You're talking like Greg Glenn, you know?
Yeah. Okay. Anyway, so okay, but what about variance of an entry in H bar? So same argument, right? But now the variance of the entries of W are 1 over n, but now H has size n. So they cancel each other, and that will also be 1. Okay. So same as variance of H bar, entry, and same argument, same as variance of F entry. Okay. So all of them are variance 1. Okay, great. So now we're ready to run SJD and see what happens. So let's okay. So let's do one gradient step. So by the way, recall the notation to simplify things. We write the gradient of the function with respect to something as d, that thing.
So actually, I'll just disturb you 1 second.
Yeah.
How we discuss in the class already? What's the big picture and all this? What all you hope to cover? How many lectures? What all you have to do?
Okay. So the big picture is to essentially cover the Gregg-Yang's infinite width limits for various parameterizations.
Okay.
Yeah.
Okay.
So
I see that's a plan.
yeah, that's a plan. Yeah.
Yeah, I'm going to take off set. You complete that, the people will be.
Good. Yeah. Okay. So yeah, now I'll do one gradient step. So you have. I think I just write down the equation on the board again. Forget. So your F was V H bar. H bar was. Yeah, I forgot that. It's a question. So, yeah, H bar is W. U. So, that's the thing. Okay. Okay, so what is this? Gradient of the function with respect to H bar. V. That will be V transpose. Yeah. And okay, with respect to H value in W transpose T H bar. Yeah. Yeah. Something happened. Okay, this is essentially similar to what we did last time. It's just chain rule. Okay, good. So now let's get to the fun stuff. So okay, so first for simplicity, let's say. Okay, so suppose we update only W. Yeah. By learning rate into the minus C. Okay, so let's say we don't update U and V for now. So now what happens? So W1 is W minus learning rate times your loss derivative times dW, right? And that's what it looks like. Okay, so now let's find out what H and F look like after one update. Okay, so what is H? So H is the same, right? Because we did not update U. So it is the same. But what about H bar? The second activation. So that will change because W was updated. So that is W1 times H. Right, and now let's see what this is. So that is so WH is just H bar minus into the minus C. DW H. And now let's recall what DW is. DW is just V transpose S transpose. So I'll just cheat here and write it. V transpose. Okay. Yeah, so that's the expression. Good. And okay, let me cheat a bit again and move this up. Okay, and what about the second activation? I mean the output. So output is V times h1 bar. So that is VH bar, which is F minus, yeah, again, you get a V there. Okay. So that's the equation of interest. Okay, and now let's recall that H had IID causing coordinates of variance 1. So from this, what can you say about the scale of the F?
N or N.
Yeah, okay, yeah. So it's indeed okay. So first of all, H transpose H is order N. Good. So yeah, so this looks like N.
N.
What about this? So again, let's recall.
V also has entries out of 1, right?
No, okay. So V alpha beta was had a variance 1 over N. So the first layer had variance 1, the other had variance 1 over N on every coordinate. So if I take VV transpose, then I have like these two rows getting multiplied. So every entry of VV transpose has variance 1. Right. So coordinates, yeah, so they look like theta 1, right? So yeah, okay, so now, so if I multiply everything out, then roughly speaking, so what's the order of the update? So F1 will look like F minus, yeah. That makes sense. Good. Okay. Good. Okay. So what they suggest is that if you want my function value, my output value to remain bounded, then C has to be at most 1. Sorry, C has to be at least 1. So C should be at least 1. Okay. And and ideally you want to set C to be as small as possible. So you should set C to be 1. So should set C equal to 1. Great. Okay, cool. Okay. So okay, great. Okay, so this is what C should be. Okay, and now let's see how the features evolve if you do this. Okay. So let's take one of our features, h1 bar. So think about my function f is b times h bar. So h bar is the learned feature after pre-output. So let's see what this looks like. So h1 bar. So again from previous equation. Oops. h1 bar minus h. So this looks like minus into the minus c. V transpose h transpose h. This is L. So this is what we had. And now, yeah, as we recall, this thing was theta n, and therefore this looked like order into the 1 minus c v transpose. Correct. And since and we set c equal to 1, so this is like order 1 times v transpose. And so coordinates of h1 bar minus h, so they have size. So roughly the size of whatever v's coordinate was, size order 1 over root n. Right. And yeah, and now for large n, essentially this will be like 0. Okay, so yeah, so which means that yeah, so you don't really get feature learning because these things stay near 0. And yeah, and if I you can also see what my function looks like. So stay close to 0. So this suggests that there's no feature learning, and you can also see it a bit more more dramatically by looking at how my function changes. So remember my function f was, so f1 minus f was minus c. Yeah.
So H was the initial step, right? And H1 bar is the first step.
Oh no, I think I made a mistake. So there's a bar here. Otherwise it doesn't make sense.
Oh, yeah.
Good, thanks.
And you are considering that L1 dash Fy into that order of n to the power 1 minus 0. Derivative of the loss function.
Yeah, I'm using the data constant. Yeah.
Yeah.
Okay, cool. So okay, so yeah, so then let's see what f1 minus f looks like. That was integrated minus n to the minus c, the grade of the derivative, the grade of the loss times v transpose h transpose h. And now the point is that this thing here v transpose, this goes to 1 as yeah, and gets large because again remember the coordinates of v were IID with 1 over n variance, and into the minus c h transpose h, this is into the minus 1 transpose h, and this goes like Yeah, and I was remember what H was U zeta. Just like so minus 1 U zeta transpose U zeta. It was right. So yeah, and remember the coordinates of U had variance 1. So that cancels with the n over minus, and it is minus 1. So this looks like this is yeah zeta square. This looks like right. Okay. So yeah, so therefore, yeah, roughly speaking, my function update. This looks like minus right. Yeah. So yeah, so basically it is like a linear update. So I'm just learning some linear function. Okay. So great. Okay. So and the reason why my learning rate is too small. So the issue is that we call the learning rate is too small. Only the first order term, because here I've ignored all the second order effects, right? I've taken only first order effects, and the second order effect will not really matter. And the first order effect will just give you some linear thing. So yeah, that's kind of the issue here. Okay, great. So this is what happens in the standard parameterization. So this is linear function. Okay, but now let's look at another parameterization, which is the mu b parameterization, and see what changes. So let's see. So here is the proposed change, proposed mu p parameterization. Okay, so here's the proposal. So you do two things, and let's see what happens. So first thing is, so you divide the outputs by root n and use θ1 learning rate. So which means that you make c equal to 0. Yeah, but if you set c equal to 0, then as you remember the previous one, then my f will blow up, right? Because if it went like anything by minus c. So therefore, you need to divide everything by root n. Okay, so you divide. Okay, so you set. Here in my v. Okay, so to be precise, in this setup. So okay, so u alpha beta that remains in 0 1, in the beginning. Yeah, for now. W alpha beta and V alpha beta. Okay, so the okay, so so as the divide output by root n, then what do I mean exactly? So what I mean is that in the trainable parameter, I will keep the same initialization. So I keep that as 0 1 over n. Okay. But my a, that I will change. So I'll multiply an additional n to the minus half on top of it. So I will so AV basically that I will make half. Okay. So yeah, so if you recall from the previous class, my actual entry of the matrix looked like V alpha beta was n to the minus AV times little v alpha beta. Yeah, so I do this, yeah, so this is what I will do. Great. Yeah, yeah, okay. And now let's see what happens. So there's one more change which I will say later. But first, let's see what the effect of this change is. There's one more. Okay, so now let's see our calculation again and see the consequence. Okay, so okay, first of all, let's see what happens at initialization. So remember earlier we had our f, h, and h bar. They all had every coordinate had variance 1. But now what happens? So of course h bar and h will nothing has changed. What about f now? So there something has changed. Because I am yeah. So now entries of f have variance. They have variance what? 1 over f, exactly. So entries of f have variance. Sorry. Variance 1 over n now. So that's the change. And earlier that is the same. Still have variance. Great. Okay, so initially that's the difference. Okay, cool. But now let's look at what happens after one gradient step. So h1 bar was h bar minus c this is what we had, right? And now this capital V bar has two components. So this is an n to the minus AV times the little v transpose. And in AV is now a half. So this is C minus a half. So yeah, order this. Yeah, I think there's a mistake.
We should plus one, right? Minus plus one.
Yeah, exactly. Yeah. Keep going. Yes, sorry. Okay. Yeah. Yeah. So now, yeah. So okay. So now if we set c equal to 0. Okay. Yeah, and now what is size of a coordinate in V? That's so coordinate size of V looks like 1 over root L because variance was 1 over L. So that'll cancel with the end of the half there. And so then this looks like 3.1 in each coordinate. Yeah, coordinate wise. Yeah, so let me stay at this for a minute. Because this is again the point. Right. Okay. Okay. Yeah, and same goes for F, right? So similarly for F, this would that as well. So F1 is F minus C minus 1. Okay, let me write one more step. C V transpose H. Right. And this thing here, this looks like into the minus 1 V transpose, little V transpose. So if C minus 1. Okay, I think I just times. Yeah, so once again, little bit transpose has, okay, this looks like what? It's scales as what? So remember, V has coordinates of size roughly 1 over root L. So this is like what?
One.
Yeah. And then you multiply that with H transpose H, right? And H transpose H looks like a constant. So this thing looks like this V transpose. think there's some dimension mistake. Yeah, I think somewhere got lost.
Praise God. You are to view transformation in case of them. But your F is your.
Okay. Don't is calling testing.
No, yeah, that's okay.
Okay. V is your.
It's zero here.
Yeah, V is your okay. So you transfer just yeah. Yeah, that's okay.
I mean, so I was hoping that this would be so so the F would update by constant, but seems to update by so for stake equal to 0, it seems to update by 1 over n.
But yeah. A is transpose A is of order n, right? So n into integral minus 1 into the
Oh yeah. I think I missed on the V and the H. Okay, yeah. I was someone thinking that's the H. Yeah, good. Yeah. Okay, thanks. Yeah, good. Yeah. I think I confused the H with the Z. Yeah, good. Cool. Okay, so yeah, okay. This is what we did just now, right? So H is U zeta, and then this is so zeta transpose U transpose U. Zeta. Yeah, exactly. And now this is this looks like order 1. And this thing has yes, n, right? Yeah, and the n will cancel with the n to the minus 1, and then so this is like n to the minus c. F minus. Yeah, thanks. Yeah, I think I confused the H with the zeta. Okay, great. So yeah, so what it suggests is that if you make these changes, then both your F and H bar will update by a constant. So you will have feature learning without blowing up the coordinates. Cool. Okay, great. So now let's also check the H. Okay, so this is for H bar, right? But what about H? So till now we have not really touched the H. So let's also do that now. So first layer, parameterization. So okay, so now suppose we also train U. So suppose we train U. So U1, U minus learning rate times your cos derivative times du derivative h. Right? It's my chain rule. And what is h1? Is u1 zeta h minus c. Yeah. And yeah, this is very constant, so we kind of throw it out. So this looks like h minus theta to the minus c dh. Yeah. And now, okay, now what was dh? So dh was again by chain rule W transpose dh bar. Was W transpose V transpose. Right? Yeah, but now we have done this 1 over root n scaling. The V transpose, so this is 1 over root n W transpose little V transpose. Okay, so now what happens? So remember we are studying c equal to 0 now. And and this is not good because you really want this h1 to also change by a constant, and that's not happening here. Right, because this dh is not good. So this goes to 0, right? It goes to 0. Yeah, and that's not good. Okay. So now, yeah, so therefore the proposal is yeah. So that's the second thing. Probably write it here. The proposal is, so you set A1. So by A1 I mean the AU to minus half and B1 to half. So yeah, by B1 I mean the BU. Okay. So that's the change. So let's see what the affects. So again by the so what does this mean? It means that I now write U alpha beta as n to the half times little u alpha beta. Right. And the little u alpha beta comes from a Gaussian. Yeah, so that's what this means. Okay. Okay, good. So if you do this, then what happens? Let's see. So we were writing U alpha beta into the half beta, which comes from. Okay, so now what? So now I claim. Okay, so now how will these equations change? So let's see. Should I just cheat and write here? Okay, it's hard to. Okay. Okay, maybe just write again. It's best. I'll just copy and write again. Can you copy this?
No, this.
You try it again. Fine, okay, I'll write again.
That's very.
Yeah, so U1 is now U minus into the minus C. Oh, sorry. So what is H1 again? So H1 is H minus the minus C. Okay, so this is what we had earlier. So now how did this change? So okay, wait, okay, let me write U first. Sorry, okay, I'm probably writing. I'm going too fast. So U1, so after with the new parameterization. U1 is now U to the minus C. Should I write in terms of little u because that's be more direct. So little u is little u initially my learning rate times your just write L times y little du. Yeah, now let's work it out. Okay, so again by this thing. So what is little du now? So that is so we will write right here. So this is nothing but root n. Sorry, this is what it is. So, okay, so what is little du now? So that is dh. Yeah. Cool. And yeah, what about DH? So blue transpose PH or right. And DS bar was, yeah, we'll just write it here again. Write the B thing also. So it was, so how did we do this? So this was 1 over root n times V. This is what we had done. So this comes. Yeah. So what's the whole thing? The whole thing is the root n cancels. Yeah. And now everything is good. Because or is it so? Okay, so C is now 0, and
Yes, one.
sorry,
Everything else is determined. Wait.
so not yet, right? Because so this is little u. So the actual u, so you have to multiply by root n on top of it. So so here my little w and little v are not order 1, right? Because
Yeah. No, you should look at H just. No.
yeah, exactly. So let's do that. That's a quantity of interest. So H1 C1 theta, that is root n little u1 theta. Therefore, that is root n u theta. So which is h. It's h minus c. Yeah. C plus a half. Okay.
What you
Sorry.
no wait.
No,
It's fine, right? Okay. Yeah, and that's what you're looking for, right? Because now you have this additional n to the half you multiplied. And therefore this whole thing is theta n to the minus c. Make sense? Yeah, so this is the crucial point. And then, so we absorb this, take a minute to see. Yeah, and yeah, I guess it's kind of a bit magical that all we did was reparameterize and somehow that solves the problem. So it's we need to digest why. Maybe to compare with the previous slide, maybe let's do the list. What happened? Yeah, so it's the exact same thing except that you get another variable, another scroll on top of it. Yeah. Okay. Okay, so yeah, so it's like the summary of what we have said so far. So if you use this mu p parameterization, which is described by the changes which we described, then that enables feature learning without blowing up feature coordinates. In contrast to the standard parameterization. Yeah, and does this even for two hidden layers? So, okay, so for one hidden layer there was the innovation, but for two hidden layers somehow because of this additional matrix thing. But this seems to do the trick over here. Yeah, and okay, so with all of this wisdom, so okay, so now okay, so what next, right? So there's a certain sense in which mu p is the maximum parameterization. I mean, it kind of so the result of Yang et al. Says that it allows you to update the parameters maximally without blowing them up. So I think intuitively you saw this. So you set your C equal to 0, so learning rate is high, and it's like as high as possible. And you parameterize your weights appropriately so that they're able to absorb this learning rate, this high learning rate. So yeah, so in some sense it looks like it's doing well, but is it really the best you can do? So in a very precise sense, Yang et al. Says that this is the best you can do. So yeah, it's a maximal update parameterization. Yeah. Okay, so yeah, I'm not defining precisely what this means, but I guess you get the gist. Yeah. So among all possible stable ways of parameterizing, so all possible ABC values, these values give you the maximum possible update. Yeah. Okay, so there's a precise way of saying what maximum update means. But I don't want to go into it. What I do want to go into is the other main topic here, which is the infinite bit limits. So okay, so here's really a big question. So ultimately, we are going to apply SGD for many steps. And now you want to understand the following. So for a large n, what is the limit of the function being learned? For your given parameterization. So yeah, that's the other question. I will state what this looks like for one parameterization, just to give you a flavor. And then we'll do it a bit more detailed in the class. So I will state the theorem now, which and explain what it's trying to say. So it says that. So here's the theorem. So say it for the mean field parameterization. Actually works also for mu p. So I just did for mu p. That's maybe the one we just did. It works for both of them actually, mu p or MFP. And for one hidden layer actually doesn't matter. So you can check that for one hidden layer, they will actually equivalent. MFP and mu p keep the same thing. Okay, so it actually doesn't matter. So it says that. Okay, so consider one hidden layer. Neural network under mu p or MFP. And suppose your learning rate is 1. So remember, we studied C equal to 0, so it's all 1. And suppose your phi prime. So where phi was your activation. So suppose phi prime is so this is what's called pseudo Lipschitz. So this is a bit of a technical term. So yeah, okay. So I'm going to say essentially what this is, but so say that your solution means that your first derivative is bounded. Pseudo means that it's kind of almost bounded. Almost means something technical. So and okay, and as m goes to infinity for every input z, ft z. So where t is the output of SGD after t iterations. So this is number of iterations. The ftz converges almost surely to ft hat z. And yes, and what is this limit? So ft hat z. So this is expectation of Z and VT Z. I think we're running out of time. Yes, so yeah, I think even if I write this, I won't be able to go into it. Okay, so maybe let me just state a corollary of this. I think that might be easier. So let's state like an easier version. So you okay, so let me not state the full thing. So just state a corollary. So so this looks like some. So yeah, so I just write some ATCT. Yeah, so these are matrices. ATCT, BT, TTC. So notice that this is a linear function of Z. Where these matrices evolve as follows. AT plus 1. PT plus 1. AT, PT, minus. Yeah, some constant. Okay, so yeah, that's the loss gradient at this limit times zeta t ct tt. Okay. With A0, D0, 1, D0, C0, C0. Okay, so this is not the full theorem. This is a corollary of that theorem. The full theorem is too long to state in 5 minutes. But okay, so what this corollary is trying to say is that okay, so consider one middle layer U network, and let's take mu p or mean field. Then yeah, so then your function learned after t steps converges to this limit, where yeah, so here you can see a bunch of matrices ATCD, PT, and TT, and these matrices evolve according to this equation. Okay, so here again zeta t is the input that is fed into the SGD at time t. So yes, that was the notation from before. So this is what it looks like. So okay, by the way, okay, so I think I forgot to say it. So this is for linear again. Everything is linear here. So field identity. I mean, otherwise, obviously, you are not learning anything, right? So learning linear functions. So for identity phi, this is what it looks like. Yeah, not sure how useful this theorem is, but Anyway, so I guess we'll continue next time. So yeah, so then next time we'll do these infinite limits in more detail. So we'll start with just the most basic thing. So first of all, even before you begin training, suppose you have these non-linearities, then what does the output look like? Even that's not clear because the non-linearities will destroy all the nice structure. So today we just assume that everything is linear, right? VW, U, and everything just worked out. And therefore this also looks nice because everything is linear, so it looks very clean. But with non-linear things, of course, everything gets much harder. So start with the non-linear discussion, and first, even without training, for random initialization, what will the activations and the output look like? So that's the, and yeah, and they will build again towards the full nonlinear limits and yeah, nonlinear mu p arguments. Okay, great, thanks.